Nice to see you all. I'm here to talk about my topic, making application rollouts observable, actionable, and boring. Before I begin, I want to introduce a little bit about myself. Hello everyone, I'm Vasudev. I'm based off of San Francisco Bay Area. And I'm super excited to be here as this is my first time speaking at KubeCon. Outside work, I love biking. I explore some Bay Area hills, and I love playing pickleball as well. At LinkedIn, I'm a software engineer on the compute infrastructure team, which supports all of LinkedIn engineers. My focus has been in the past 2 years building a LinkedIn's Kubernetes platform that serves the stateless applications with focus on observability, reliability, and mainly developer experience. The compute infrastructure layer itself comprises of 500,000 servers running 3,000 applications inside 1.5 million containers. And these applications are changing at the rate of 50,000 rollouts a week. When we look at closely how is the platform being utilized, there are mainly two personas which are beneficiaries of this platform. Meet Alice, who's an application developer at LinkedIn who focuses on building application features. Meet Bob, he's a platform engineer who builds and operates the platform that runs these applications. When Alice develops new code and deploys it to production, they typically have these questions. Hey, I just wrote a new piece of code, a new version is built, it's deployed to production, did it succeed? Or if not, why it did not succeed and what can I do about it? Bob, on the other hand, who governs the platform reliability, is interested to understand the overall platform health. So the typical questions are, how's the platform doing? Are the rollouts succeeding? That might be a great measure specifically in the perspective of application rollouts. But here's the tricky part. When you enter the world of Kubernetes, the Kubernetes is always converging. Answering these questions becomes a bit more trickier because Kubernetes is declarative and always converging. So that means when you change the desired state, it is going to continuously reconcile forever until that desired state is met. This translates into a fact that there is no native notion of, hey, there is a rollout done. This is the final state or a terminal state that you can take a next step forward from here. In other words, if Alice asked a simple question, I click deploy on some UI, and did the rollout succeed or fail? Answering that is not a simple yes or no question. That means you need to get data from look up YAML files, look up events, look up logs, and imagine doing this thousands of engineers doing the scratch investigation all the time. This means the team, Alice and Bob, are in the state of constant debugging. And that's operationally expensive and not sustainable. So today I'm here to talk about how we built a system that answers these questions, but also provides the best platform and developer experience to Alice and Bob by making the application rollouts observable, actionable, and boring in a good way. So let's take this step by step. Let's dive into how we make application rollouts observable. Making application rollouts observable really means is that we give every rollout or every change an identity with context that removes any ambiguity about what is the change about. Essentially, it's about answering these questions. Who made the change? What was the change about? And when was the change made? And what was the outcome of that change? At LinkedIn, we use Kubernetes as the building blocks of our platform. And on top of that, we have custom resources that the developers interact on a daily basis. So every rollout essentially begins with one such custom resource. We call it LI deployment or LI deployment. An LI deployment is a CRD that captures the developer's intent in the form of, hey, this is my application, it's running with some version, this is the number of replicas I need, and these are the number of resources. The platform then takes over from there and orchestrates a safe and reliable rollout in the clusters. To give you a sense of scale, the user would provide typically about 10 to 15 lines of YAML input, and the platform expands that into about 500 plus lines of pod spec by injecting all the platform-specific settings to make sure that the application runs correctly in production. Now, when I say rollout, what I mean is really the entire journey of a change, right from where a configuration change was made on the LI deployment, all the way until the new pods are created, initialized, scheduled, and then the containers becoming healthy and eventually converging in the clusters. Now, one of our goals was to make all of these rollouts observable without any ambiguity. So we want to but the rollout signals are actually scattered across the cluster. We have events in one place, logs elsewhere, the status field somewhere else. Now, with the scale that we had, the information is probably leading to chaotic. Like there is just too much information, not really, we cannot process it well. So one of the first things that we did was we converted that chaos into a structured stream of events, each event being represented as a top level external entity we call an intent. So in this output, this is the outcome of how the rollouts were made observable. So each row here represents an intent, and it has everything you care about, like who created the intent, what application it belongs to, when did it start, and finally what was the outcome of it. Did it succeed or did it fail? The next couple of slides, we try to understand how we come to this stage. So much of this rollout context that you see in each row is embedded right inside the LI deployment resource itself. In order to capture the context right in the beginning, we add annotations using the LI deployment's mutating webhook. And the first annotation we add is an ID. We call it an intent ID. It's basically a unique identifier for a given rollout. The ID is actually repurposed from the Kubernetes admission review request, because the ID is generated the moment the request hits the API server before it is even persisted. So we get to tie the LI deployment mutation to a specific rollout right at the creation time. The second annotation we add is the intent username. That's simply answering the question, who initiated this rollout? So if you think about the changes, they come from a lot of different places. It could be from a deployment UI where a user clicked deploy, and then that triggered a series of workflows, and then the code get eventually deployed. Or it could be through command line interfaces like kubectl, somebody made some ad hoc changes on the object directly in the cluster, or using some internal tools. And finally, we have the platforms and integrations that build on top of LI deployment using their own custom controllers. So by capturing the initiating user for every rollout, we essentially anchor the rollout to a clear owner. The third annotation we add is the intent start time, essentially answering when did this rollout start. So it helps in two purposes. There is one that we get to build a timeline of rollouts. Okay, these are the series of changes happen, eventually turning into a rollout history for that application. And also when there are symptoms of failures occurring for the application, we can now correlate, okay, the rollout started at this time, and I can clearly correlate that with an error rate that spiked. With this, we can tell that the rollout started at X time, but how can we tell that when it's actually done? Remember the problem that we just started with, that Kubernetes is always converging. It's going to keep doing its job. Maybe the pods are crashing, they're not healthy, but it's going to say it's doing its job. But systematically, we need, the users and systems need a clear terminal signal to basically trigger what comes next. Say if the rollout has failed, you might want to automatically roll back to reduce the impact. Or if it is succeeded, you might want to run some validation workflows that make sure that the new version hasn't introduced new regressions. To support this, we adopt a similar mechanism that the Kubernetes deployment does, that is the progress deadline seconds. Essentially a timeout that tells us how long are we willing to wait to make progress. And if you're out of that timeout, then we fail the rollout as timeout failure. The real-time rollout status is reflected in the LI deployment itself in the form of a condition. We call it rollout successful condition. It transitions between three states, just like the Kubernetes style state is unknown, true, and false. If there is any progress detected in the rollout, that means the new pods are created, old pods are deleted, then the rollout successful condition status is set to unknown, that there is a progress happening. And then if the desired state is met, that means we've already achieved what we wanted to do. The number of desired replicas are equal to the actual replicas, then the status is true. It's easy case. But when there is a timeout, that means no progress has been detected for the progress deadline seconds, it's timed out and the rollout status is set to false. Let's put this all together into a rollout instrumentation and see how this all fits together. So we have clusters running different LI deployments. Users, humans or automated systems are going to make changes on them. We have a webhook, like we discussed, which is going to capture some context about this rollout and add annotations to it, like the ID, the start time, and the username. And from there, the controllers take over and reconcile them into the actual pods in the cluster. In the meantime, we also have the rollout status calculator, which is going to reflect the real-time status of the rollout in the rollout successful condition, whether it is true, succeeding, or false. Now the controller is also going to emit the life cycle events of particular rollout. Is it progressing, is it succeeded or failed, in the form of Kubernetes events. So these events are captured by an external entity called events consumer, which is going to convert that into the top level entity we discussed called the intent. That is an offering from the deployment orchestration service. And that ultimately is what powers the UI, where users can see a clear, intuitive way of all the rollouts, including its status and history. So to recap, this is the rollout material that we just captured. We have the 3 annotations, and we have status conditions showing whether it is succeeded or false. Now, if you take a look at the right one that I've highlighted, the status says false. Sure, we now know that the rollout has failed, but it's not really enough, because what users really care about is, why did it fail? So that brings us to the next step, that is making rollouts actionable. Essentially means that we want to turn every rollout failure into a clear next step, no matter what the change is. It's about answering the questions: why did rollout fail? What's the fix, and who is going to fix it? And we start that by transforming the rollout condition itself. So remember, we had the rollout condition like this, that there is a status false, it says the progress deadline exceeded, and the message basically says the rollout timed out. We transformed from this to something like this. So in here, the message clearly says in plain language, why did the rollout fail? And there are also clear next steps. So if you look at the condition, we have an explanation about human readable explanation of why the rollout failed, and then the concrete next step just below that in the form of, hey, go run this CLI if you want to learn more, or go read this documentation to understand further. The next few minutes, I'll deep dive into how we built this, and then later we'll come back into like what would be the user journey look like when they follow the suggested next step. Now, if you think about the rollout failures itself, they can happen across any layer of the stack. So right from where the LI deployment is updated, all the way until the pods are changed, the rollout failure can happen any layer and anything in between. So we needed a consistent, clear, and a plain language to represent any rollout failure. That's when we introduce our own failure reason taxonomy. It's basically a structured classification system for any possible reasons why a rollout could fail. It turns the scattered Kubernetes signals into a common vocabulary that can be both human consumable and programmatically be dealt with by different applications. So the taxonomy is simple. We have the top level category, which explains the overall category of failure. And then we have a reason that gives one word reason for why the rollout failed. And we have a message which basically is going to give a detailed human readable explanation of why a rollout failed. Now so here's an example of it. The message basically says the application failed to start. Clearly the failure category is application. The application failed to start is the reason. And the detailed message gives, hey, there is one pod that's been failing because there is a container running certain version of an image, and it's been crashing with an error reason like exit code 1. Now building this message can be straightforward depending on where the rollout failure can happen. So if it is at the configuration layer, it's clear that there is a user input. But if it happens at the pod layer, things get really involved. Pod lifecycle goes through a really complex journey, like there is scheduling, there is creation, there is image pulls, there is init containers, there are probes, and so on. And the failure can happen anywhere in this chain. So we take a failing pod, look at its conditions and container status, and convert that into a structured failure we just discussed in the form of 3 fields: the category, the reason, and the message. So here's a quick rundown of how we do that. So when we see that the pod isn't ready, one of the first things we check is whether it is actually scheduled. The pod might not even be scheduled. So that means if there is not even a node to run this pod, it's probably an infra failure at this point. So if the pod is scheduled, we check if we ask the question, has the pod really begun? That means if any of the init containers are started. So to capture that stage, it is categorized as pending pod initialization. If not, we check if all the init containers have completed successfully. Any failures at this phase will be categorized as initialization failure. At this point, the main container application image starts downloading, and depending upon the size of the image or the network delays, it might take certain time. So to capture that phase, we categorize as waiting for image pull. And for some reason, if the download fails, we call it as failed to pull image. At this point, typically the application container has everything it needs to start the application. From here, we deep dive into the application container, see its container state, whether it is running or terminated or there is a restart count, and then we typically categorize it as app failed to start if it is unhealthy. So all of these rollout signals, the 6 of them that we've seen in the screen, are exposed as part of a common library that gives us a consistent mapping of a signal into a failure reason and a category. So in this example, we have seen the pods unschedulable will be mapped to infra, and app failed to start will be mapped to the app category. Here's an example of how a failure pod categorization look like. So on the left, we have a representation of a pod. It's not ready, it is scheduled, but it is clearly not initialized, as we can see from the condition. And that translates to a message something like this, where the category is infra, it's initialization failure, and the message says what init container was not ready and why was it crashing. In this example, we can see that it is being killed. Let's put this back into the overall architecture we were just discussed. So we have the rollout instrumentation. It is exactly the same what we discussed. But in addition to that, the rollout status calculator has a new add-on component that let's call it pod failure summarizer. So whenever a deadline occurs, the calculator is going to invoke this module where we scan all the not ready pods, categorize each pod into its own failure reason, and then it is going to group and create an aggregated rollout summary message. So with that, instead of looking at a bunch of noisy pods, now we have one clear message for every rollout failure. That's about building the rollout failure message. Now let's take a step back and walk through the user journey, how they would follow the suggested next step. So if you think about what Alice would do, they saw this failure reason, they got some context about what happened. Now they want to understand more, they already have the clear next steps. One of the first things that Alice would do is run kubectl in status li deployment, the command that is just highlighted there. That's the muscle memory that we have built for most of our engineers. So kubectl is an internal kubectl plugin that keeps things familiar. So it hides the Kubernetes complexity, but preserves the muscle memory because they want to have the consistent experience even though the underlying platform is evolved. So the output of this command line will give additional information and context required, like statistics about the pods, containers, init containers, metadata about the namespace, clusters, and so on. Instead of stopping right there, we also have a link to an all-in-one dashboard which will provide the rollout signals as well as the application signals in one view. So Alice would land in one page, a page like this, where they would pick one of the LI deployments they're interested in, and if you drill down further, you will eventually reach a view specifically meant for a pod that they're interested in. So even in here, we have a simple representation of the pod's lifecycle about the timeline when it was created, sharded, initialized, and so on. We also have tabs for metrics, logs, events, and even application logs. So just like in the condition and in the CLI, we don't let the users guess what next. So before in the condition, we had the next steps. In the CLI, we had the next step, hey, if you need more information, go click this link. Here we have like pre-formed kubectl commands specifically tailored for that pod. So in case they want to understand further, they don't have to go, what was that command again? I forgot, maybe I forgot the flags. They just copy the command from here and then they go right in. So this is the pattern, like we don't let users guess what's next. And when the metrics tab leads to a page where we have an integrated view of all the metrics that are like related to Kubernetes signals, the application signals in one page. So here are some of the examples, like we have the status of the rollout, we have the desired replicas, we have the number of ready and running pods. Some of these alerts, some of these metrics are packaged into a set of default alerts, so that every application in the platform get them by default. So what this means is that even when the application the rollout hasn't failed, the users get notified immediately when there is something wrong. So what this means that this is the observability is not just bringing visibility, it is actually bringing awareness to the application owners that there is something wrong already. Now this is about the user's perspective. But if you take a step back and zoom out, now that we have the categorized failures, you get to build a story of how the platform's doing. One of the first things that we would start is thinking about what are the failure categories happening across the platform. Is it application, is it infra, or is it unknown? So the uncategorized failures is also actionable to us because any unknown failures is like a blind spot. That might mean there is an unknown state of the application which is crashing, which we do not know what's happening, and that is something we don't like. And for each of the categories, we deep dive into what is the distribution of failure reasons happening within the failure category. So in this case, there are app failed to start, majority of them, but there is also an invalid LI deployment. So even though this is a user input failure, this also gives us an opportunity to think that, okay, there might be a guardrail missing that's causing the users to do this mistake. So that becomes an actionable to our team. Similarly, for the infra failures, we try to understand the distribution. With this, we can understand which areas of Kubernetes and platforms needs optimization and which one needs to be focused on. So with that, we understood what kind of failures are happening and what were the reasons for the failures. We also try to understand where are these isolated to. We use a visualization something like this, so where we can understand, okay, there is a pod unschedulable failure, perhaps limited to region 1 and region 2. It also tells us that the application 1 and application 2 are the most affected one. So this gives us a clear next step, similar to what we gave next step for Alice. At the end of the day, if you remember the first slide, Bob, the platform engineer, cares about how is the platform doing, how often are the rollouts failing happening. So we've built a metric called rollout success rate, kind of a true north metric for Bob's team, where this graph plots the rollout success rate over time. And whenever there is a drop in the rollout success rate, the vertical bars beneath it gives us the root cause of why the failure happened. Here's a quick example of how a drop in such a rollout success rate drives the platform improvement. There was one time when there was a sharp decline in the success rate. About 55% of them were failing with some rollout timed out. But because we have this observability and actionable components built into place, we were immediately able to tell that it was mainly due to the image pull delays. And then we pulled in our partner team to inform that, hey, there is rollout failures happening, and we think it is due to the delay in downloading the images. The team investigated and found out there was a faulty node in one of their servers serving the images. They had some CPU contention. They immediately fixed that. Along the way, they also found some optimization they could do on the cache TTL. So this is a clear example of how the observability on the application rollout side drove a platform improvement. Now that comes to the final stage of making the application rollouts boring. They are reliable, they work, they just work. This is no accident. This is an outcome of an exercise being done over and over again. So you find some problem, you see that you couldn't tell it before, you make it observable. And if you make it observable, you decide what to do next. You make them actionable, make this fix. So it's about you find a problem, you clearly understand the problem, you know what to do next. If you do this over and over again, I think the outcome is predictable rollouts. Essentially, will look like this for Alice and Bob. For Alice, there are no surprises. Rollouts are a non-event, they just work. And even if they fail, there is no Kubernetes guesswork involved because they have all the tools necessary to debug themselves. That translates to if they were spending hours of time debugging before, now it's just probably minutes. And for Bob, I think the focus comes back to innovation, the lesser interruptions because it's all self-serve, and the expectation of rollout success rate to be 99.5% is normal. It's a routine. And the rate of unknown failures is also reduced to 0. Here's my personal experience of this entire journey. So I remember there was a time when somebody walked up to me and said, there is a rollout failures. I might have gone like, oh, not again. But today that's different. Today when somebody walks up to me and says, there are rollout failures, before they even finish the question, I would have already known what was the reason for it. I think that's the moment I realized that the platform is doing its job and the observability is on the right track. Here are some key takeaways from this topic. So the observability starts with identity. You have to give every rollout owner a timestamp and a reason, no matter from where they come from. But you shouldn't just stop at visibility, like aim for meaning. Observability without making it actionable is just data. I don't think that's useful. So knowing what failed isn't enough. You have to know clearly why that happened. And finally, abstract Kubernetes. I think this is the one that goes a long way, where you saw examples of how we've integrated the application and Kubernetes signals in one place through the integrated CLI and the UI experience. So that empowers the developers to do self-service debugging that saves your time to build some interesting and build the platform itself. And the final key takeaway from my talk is that observability isn't about adding metrics. It's about making your system explain itself. Thank you so much for listening to me. What you just heard from me from the last 30 minutes is just the part of the puzzle. So we had our team, Ronak and Amit, present in EU this year about the overview of LinkedIn strategy to adopt Kubernetes in its compute platform. So feel free to check that out. There's a QR code here for feedback for my talk. I'd love to hear what you all think. And finally, we are hiring. So you can let me know in the message or scan this code to drop a message to our partners. Thanks so much for being here.